Okay, welcome everybody to more data mining. There's another notes packet to pick up and quick announcements about the midterm. Midterm, you're getting it tomorrow. Hopefully people are on the way to being ready for that. If you feel like you're still on the way and not all the way arrived at the destination of readiness, tomorrow before giving out the midterm, I'll have more review sessions, 10 a.m. to noon. And then after the review session is over, I will just walk back over to my office and upload the midterm to GitHub. So it'll be uploaded sometime around noon tomorrow. Submitting the midterm, you'll have several different options. If you prefer to work on it pencil and paper, then you can do that and give it to me pencil and paper. If you're working on it over the weekend, again, the due date of the midterm will be Sunday at midnight, or I guess Monday morning when I first get into my office. If you want to do it physically, slide it under the door, that's okay. There'll also be a Sakai upload thing that if you want to do it electronically, complete electronically, then you can just do that and submit it up there. Or if you complete it before Saturday, then you can just walk into my office and hand it to me in person. Any option, any of those is okay. Any questions about midterm, what to expect for the midterm? Everybody's 100% ready for the midterm? Lots of no's, yeah.
Can we discuss questions with you after class?
Question is, can you ask questions for me after class? Yeah, I think I have a meeting at 3, but until then, I'll be open for questions. Okay, then today we're continuing talking about the textbook, the chapter 1 of the learning problem. Last time we started talking about the PLA. No, it's not the People's Liberation Army. It is the perceptron learning algorithm. And we ended up talking about something exciting's happening. Working on the runtime of the algorithm, and there's all these weird sort of quantities over here that we'll explore a little bit more about today. We did the part A and B of that problem, and we ended up on problem part 4 right here. And so this will give us a good sort of start into the difference, or a little bit sort of kind of review of the midterm material. None of this stuff is going to be on the midterm, but this problem is asking us to compare the runtimes of the PLA with the power method. And so that'll help us review maybe the power method a little bit. And yeah, so here we go. So there's 3 things that we're going to highlight. The first one, and maybe just up here at the top, I will review for us what the power method runtime was. That's the O of the log epsilon over log alpha times the NNZ of P plus N, something like that. That's the power method's runtime. And in particular, it was sort of divided up into 2 parts. The first part where we had a bound on like each individual iteration. On each iteration, for the power method, we had a specific bound on like how good is our accuracy going to be on that particular iteration. And it looks something like X. I think they're using the superscripts T plus 1 minus X. T was less than or equal to, let's see if I can alpha to the k, or in this case, t, since I'm using t. We'll change that into a t. Something like that is what our bound looked like. And so if we stop the power method like early, like we start it and then we realize, oh, this is going to take days and days and days, and I don't have days and days to compute, then if we stop early, we still get a guarantee that so we get some sort of guarantee on our solution. So that's the idea of this first difference right here. If we stop early, there's still some guarantee on the solution. This property is sometimes called it's an anytime algorithm. Because we can stop it at any time, and it's not going to be as good as if we ran forever, but it'll still be something decent probably. This is all about the power method. For the PLA, we have no such sort of guarantee. The PLA, we know that we were somehow probably getting better on each iteration since eventually we converged, but PLA only a guarantee at the end of the algorithm. And at each iteration, there's no guarantee that if we run only 50% of the time that our solution is going to be 50% as good. So that's the first of these differences. Number two, the power method is never going to reach. So it's this anytime algorithm. We can stop it whenever we want, but it's also never going to reach an optimal solution. X sub t or super t for any finite t will not be optimal, will not be equal to the page rank vector. It'll get close. In every iteration, it'll get closer and closer and closer, but it'll actually never reach the exact page rank vector. And it turns out that under any sort of reasonable model of computation that you have, there is no algorithm that will that can compute the exact page rank vector in a finite number of steps. So we're never going to get exactly there. The PLA algorithm, though, after we complete the number of steps that we've been allocated, so after t greater than or equal to our formula was this r squared over rho squared w star squared like that, after that, we will have some sort of optimal solution. This property that we're never going to have exactly the right solution, but just approximately the right solution, sometimes makes the PageRank algorithm be called an approximation algorithm. We're always going to be just like this little epsilon off. Question?
So because the PageRank vector is just like the steady state solution to the key matrix, it
Right.
would be like possible to calculate it, right?
So the question is it possible to calculate it in theory? And the answer is that in general, using just additions and multiplication, subtraction, division, the sort of like standard arithmetic operations, it is not in general possible to calculate it exactly.
Like, could you just like do it solve like a matrix? Like,
so you could maybe use like, okay, we're not going to implement the power method. We're going to go over to LAPACK or some other thing that implements computing the top eigenvalue. And the top eigenvalue or the top eigenvector has no analytic solution. That they're all somehow approximation algorithms like this.
So like, yeah, so but we choose, so it's not it wouldn't be perfect, but it would still be, that would be closer than x to the k, but it would just cost more.
Yeah, so you can get your solution within arbitrary accuracy. Like however accurate you need for your problem, you can get it within that accuracy. And internally, LAPACK is going to use, it might use the power method. It might use something slightly different. It makes no guarantees about what method it uses, but internally there's going to be that same sort of accuracy runtime trade-off. And that's a fundamental trade-off that you can't get away from that particular problem. Does that answer your question?
Yeah, I understand that. Thank you.
Good question. Any other questions so far? Okay, then the last thing is, and this is getting a little bit more technical. So with the power method, there's a couple of these quantities that, well, all the quantities we know in advance. We know epsilon and alpha and NNZ of P and N, all the things that go into our runtime formula, we know those values. Without doing any calculations, that's just like given as part of the problem. Some of these we get to pick. And these ones, we don't get to pick, but we know them. With the perceptron, so the quantities that we depend on are the R, rho, W star, and then D, the dimension of the problem. These top three determine how many iterations we do. This bottom one determines the price of each iteration. And the dimension, we definitely know this in advance. This R quantity, so the radius, we guess we could conceivably calculate it if we wanted to, that the radius, again, I'm gonna scroll up just so we can look at the definitions of these things a little bit. The radius, you do a for loop over all the data points, calculate their L2 norm. So we could calculate that. It's not something that's usually like, you never explicitly calculate it, but we could calculate it if we wanted it. But this rho value and this W star value, like W star is the thing that we're trying to calculate. And so we can't possibly know that in advance because that's what we're trying to calculate, is compute one of these W stars. And rho depends on W star. So the W star and the rho, there's just no possible way to even know those in advance. The rho and W star. Impossible to know in advance. At the end of the problem, when we are totally done and we've computed things, then we would have access to the W star. That's what we're computing. And so we would be able to compute the rho if we wanted. And so we could compute what's the bound on our runtime after we've already computed everything. But there's no way to know what the runtime is going to be before you're actually completed with the problem. Again, that's in contrast to the power method in PageRank that If I know that I really need a faster runtime, then I can adjust the alpha or the epsilon parameters. Or if I know that I can, maybe everybody's going on vacation for the next 2 weeks, so I can let the computers just churn, run away, do all their calculations, I can adjust these parameters to adjust how long the runtime is going to be. But not only can I not adjust the parameters in the perceptron algorithm, I can't even know what they are in advance. So this begs the question about, like, why did we even care about these parameters, these values here? If we can't even know them in advance, then what's the use of like having this runtime guarantee? And that's what we're going to talk about in this next problem down here. We're going to look at some different data sets that have these different R and rho and W star values, and we'll get a sense for what kinds of data are slow and what kinds of data are fast, so that we can think, okay, our data probably fits into this certain category of things, even if I can't prove that exactly. I know it roughly has this shape to it, and so I think it's probably going to be fast. Or if I modify the data in a certain way, I can cause it to be faster. Before we do that, any questions just on these differences between the algorithms? Everybody's brain's only thinking about the midterm right now. Why are we talking about this? I want to know about the midterm. Okay, so the runtime again, so what this problem's asking us is, based on that analysis above, we're going to draw some different data sets and see how they're going to have different runtime properties. And so again, the runtime, PLA divided up into 2 different steps. Basically, all the runtimes of everything we're going to consider divided up into these 2 steps. Think about the number of iterations and the price, the cost of each iteration, or the runtime per iteration. The perceptron learning algorithm update was only a single inner product or a single vector operation, had the O of D runtime, theta D runtime, which is also O of D. And so by changing the number of dimensions, I can change the runtime. Usually, though, we don't really have control over the number of dimensions. That's something that's sort of given to us as part of the problem. And so the more interesting things are going to be up here in controlling the number of iterations. And again, also, this is specifically asking us to draw 2 data sets. So I can't draw in 3 dimensions, but I can draw in 2 dimensions. Drawing in 1 dimension is a little boring, so sort of stuck with D equals 2. So the number of iterations, again, saying that the number of iterations T is less than or equal to R squared over rho squared that. And this is just copying down the formula from above. So what we need to do is we need to think about how can we control these quantities, or when we draw our pictures of our data sets, what factors in that picture affect these different quantities right here. So let's remind ourselves, like, just what all these terms mean in picture form. So I'm going to draw a data set with the axis here. So that's our 0 point right there. And then let's add some pluses for all the positive points. The location of the plus, again, is the x value of our data point, and then whether it's a plus or minus is the y value of the data point. So we have some sort of data set like this maybe. And then the W star is any optimal hyperplane separating the 2 of them, any line that you can draw that linearly separates the pluses and the minuses from each other. Like so. I drew one here that's particularly nice, sort of high separation from both of them. But if I were to move that around, as long as the pluses and the minuses stay on the same side, it's still okay. So that's what the W star is. The rho, switch here to orange. The rho, again, is if you take the distance from your W star, your hyperplane, to the closest of those data points. In this case, I drew them so they're all basically the same, but whichever one is the closest, that quantity right there is equal to rho divided by the norm of W star. So that quantity right there is sometimes called the margin being the difference, the distance from your separating hyperplane to a data point. And I'm going to go ahead and give us a special name for that of gamma. The book doesn't use this gamma variable, but it's convenient to talk about both of these two things together at once. So I'll use gamma right here. Gamma equals rho divided by W star. And the reason for that is now if I plug in the value for solve this in terms of rho, so it equals gamma divided by W star, plug in for rho, then that's equal to R squared over gamma squared. So that formula right there, not in the book, but I think it's a little bit easier to think about this one since the rho divided by W squared has this sort of geometric interpretation. And then the last of the important quantities is the radius of the data set. So typically visualized by drawing a circle around whatever the largest data point is, but it's really only the largest one that you care about. And the distance from that largest data point to the R origin is your radius R, like that. So when I'm thinking about the runtimes of my perceptron learning algorithm here, I have these two variables, this R and this gamma that I want to control. And so if I make R bigger, keeping gamma the same, then I'm going to get a slower runtime. Make this bigger up here, keeping this the same, then the total number of iterations will be bigger, so it'll be a slower runtime. Drawing that out over here. So I'm gonna try to reproduce this data set over here with some pluses like this, but I'm moving them really far away so that the R is gonna be bigger and the minuses this, but moving them really far away so that the radius is bigger. But if I draw my W star like this, then that gamma value gamma is the same, but that R value is now, let's just go ahead and add some more pluses over here so it's totally obvious that the R value is bigger. Drawing that circle like that. And now the R, much bigger. So I'm gonna somehow be needing more runtime to work with this data set than this data set. And so even though yeah, again, even though I'm not necessarily calculating these things in advance of my problem, if I have a sense that like, oh, the data points in this data set are really, really big compared to what I'm used to, then I should expect the runtime to take longer because the radius of the data is going to be bigger. Any questions about that? I'll make sure I explicitly say right here that this will be slower. And so sort of by the same argument, if I were to draw another data set with the same radius, I'll do it with the same R as up there. So it's the pluses are all really far away from each other. The big R is much bigger. But now the pluses and the minuses are all like sort of really close to each other. like that. That gamma distance is smaller. Yeah, maybe it's not to scale, I don't know, but this is supposed to be smaller, the distance between the green line to the negatives and pluses. We'll add some more. Just right on the border here, really make it small. And that is also going to, the smaller gamma will also cause the larger runtime. So it's a same R, smaller gamma, larger runtime. And this is separating these two things, other things. So either those two sort of transformations to the data somehow make things slower. Yes. It is a great question. So the question is, over here on a plot like this, and I'll just do it in a separate plot. If we have the same looking pluses and minuses like this, what if I drew, say, maybe a worse W star like this, where the gamma for this W star is going to be much smaller. The margin for this W star is smaller. That value right there. Very small. And the question is, now, does this have a worse runtime because the margin is smaller? And the answer, which is a little bit subtle, is that this formula right here holds for any possible W star. So it holds both for this W star with the larger gamma, and it holds for this W star with the smaller gamma. And so if we try all possible W stars, we'll get some of them have small gammas, and so we'll have imply a large runtime, but some of them will have larger gammas and will imply a better runtime. So it's this sort of factor right here in the runtime is not something that we affect at all with this sort of scaling or our choice of W star. It's just like whatever the best possible W star is. Does that answer your question? Good question. So these are all things making it slower. Let's just do one last example, making it faster. The sort of canonical example is now if we had all of our pluses and our minuses sort of super far away from each other like this, then the best possible of those W stars, somewhere in the middle, huge gamma. Large gamma, so it has the same radius, and those two things together will imply the faster runtime. And sort of the intuition of this picture is that now we have there's more freedom, more leeway in selecting a W star. So you're more likely to hit one of the optimal W stars earlier because there's just more possible things to hit there. Any questions on any of these? Okay, then So problem number 5, here's where the things start getting into like actual like interesting problems about the perceptron learning algorithm and data sets and what you might want to do to the data set to try to make the analysis of that data faster. And so in this case, the hero today is Alice, and she is proposing some, I've got 3 different variations on the perceptron learning algorithm here that she's proposing, and we'll see that some of these are faster and some of these are not. And we'll go through the first one of these together, and the other ones you'll get to do on your own. So here, this transformation, the suggestion is that if we do, instead of directly running the perceptron learning algorithm on the x's, we know that the radius of the data somehow affects the performance. So let's try to shrink the radius of the data somehow. Let's take all of our x's and divide them by some constant alpha, some number that's bigger than 1. So we're going to shrink the x's, make them smaller, make the radius smaller. Our new radius, r prime. So the radius is just defined by the max over the i's of the x sub I, like that. And since so the prime right here indicating that it is a the modified data point. The modified data point max over the i's defined to be the original data point divided by our alphas like this. That alpha can come out of the max. So 1 divided by alpha max over I norm of x sub I, like that, is equal to 1 over alpha times r. So if you just shrink all the data points by this alpha factor, then the radius also shrinks by this alpha factor. And so the question is, then that seems good. Like, we know that r somehow controls the runtime. If we use have a data set with a smaller r, if we can somehow massage our data into having a smaller r value, then we'll get a faster runtime. When we do this, though, we'll also have to think about not just the r, because the runtime, again, less than or equal to r over gamma. We have to think about how does this transformation affect the gamma. And so here, the gamma, just by the definition of it, is the minimum over I, y sub I, w star transpose times x divided by the norm of w star. This is the definition of gamma. I haven't done anything special right here. Just the definition, this top quantity, the thing above the numerator. This thing is the definition of rho from above, and then gamma was defined as rho over w star. Well, when I do the, and again, I guess this should be the x prime right here because this is the gamma prime. When I do the substitution of x prime for the regular x, according to this formula, according to the transformation that we're doing, it'll be the minimum over I, yi, w star, transpose x divided by alpha divided by the w star, like that. Here, this alpha factor again doesn't actually affect the minimum, so we can pull it out. It's a constant for all the different i's, so we can pull it out, and we get the 1 over alpha up front, minimum over the i's, y sub I, w star transpose x sub I divided by, so much writing, w star norm, like that. And then this thing on the right-hand side over here was exactly the definition of gamma. So it's gamma divided by alpha. It's a lot of just writing out sort of the definitions, chasing the definitions of these formulas up here, so that we can just rewrite what the new radius of our data set is in terms of the old radius of our data set, and the new margin of our data set in terms of the old margin of our data set. Yeah, there's nothing particularly fancy going on inside those manipulations. But then the point is that we want to compare the total number of iterations of the original data set with the new data set. And so the number of iterations on the old data set was again less than or equal to R divided by gamma. Number iterations of the new data set less than or equal to R prime divided by gamma prime, which now we have formulas for R prime and gamma prime. We can plug it in. So 1 over alpha R divided by 1 over alpha gamma. The 1 over alphas cancel out, and we still just get R divided by gamma. So the highlight here is that these two quantities are exactly the same. The number of iterations for the old and new data set. These are the same. And so that implies that we get no speed up. From doing this transformation right here. Again, the R and the gamma values, they're not things that we can really actually know about the data, but nonetheless, using this runtime guarantee that we have about the PLA algorithm, we're able to show that by doing this transformation of the data, by scaling the data by any constant value, it's not going to actually affect the runtime. So if for whatever reason that's a useful transformation for you to do for other reasons, you should feel free to do it because it's not going to affect things, but you're not going to be able to use this transformation to make things faster. A lot of the things that we're going to talk about over the next, say, month or so in this class are sort of sitting at this level of abstraction where there's going to be a lot of these parameters of the problem like R and gamma that we won't know what they are. We won't know, in some situations, we will have no possible way of calculating them, but still we'll be able to work with them and show that even though we don't know what these values are, we can use them to show that transformations of our data are either good or bad for computational or statistical purposes. Any questions about any of that? Okay, there's two more problems in this note packet. One of them does result in a speed up. One of the transformations does result in a speed up, and one of them does not result in a speed up. Yeah, recommend working through those. So that's the last about this note packet here, and we'll move on to the one for today. Learning problem number 2. In that first packet, all we did was we talked about purely computational things. We didn't talk about anything statistical at all. We assumed that our data set in various ways was particularly easy, so there was no need to talk about statistics. This sort of last half of chapter 1 here, we're going to start talking about statistics, and we'll see how, that'll be combined with our runtime analysis eventually. Today and probably the next couple weeks, we'll be leaving runtime behind for a little while, focusing just on the statistics, and then we will get those two concepts merged together in a couple of weeks. So the first problem I have listed here, again, sort of a little bit of reviewish stuff from the first part of the chapter that we talked about a little bit about the difference between learning problems and design problems. Something that you'll want to make sure that you understand for the next midterm. And there's this exercise 1.5 that has a bunch of examples to go through. We already saw one example of a good learning problem. A good example for learning was when our X is that banking problem, the credit lending problem. X is information about a person. The Y was whether we should lend to them or not. And the y's, again, always are equal to the f of x by our formalism. And this f function right here, this ground truth function, something that we don't know in advance. And there's no like conceivable realistic way where I can write just a straight down algorithm and know that that's going to be the perfect answer. So no way to know that in advance. In advance. Example of a problem that would be bad for learning or good for design would be if determining whether a number is prime or not prime. So x just is a number, y, is it prime? We already know what the formula is for this f function. You just loop over all the numbers, checking to see if it's divisible or not. So we know the formula for f. And so there's no learning to do. Any situation usually involving, I don't know, physics or mathematics or things that we already have like somehow formulas, analytic solutions for, not used for learning. It's only these situations that are somehow really, really abstract, not things you normally talk about in math classes or science classes, things that you talk about in more softer sort of subjects. So one of the main purposes of this is to remind us again a little bit more of our formalism of all this different notation, especially this f function right here, that in the previous note packet, we always assumed that the y values directly correspond to some function of the x values. And now we're going to start talking about a slightly more complicated formulation of the learning problem that will be much more practically useful. It's in the book in sections 1.3 and 1.4. We'll talk about those combined together. And there's this figure 1.1 that we're just going to sort of draw from scratch, going over what all the parts mean. And so this figure has a bunch of notation inside boxes. And so I'm going to start with all of our existing notation that we had some target function or ideal function or the Bayes function, this f, and goes from some set of x's to y's. And then we had some data points, training data, which is all these like xi and yi pairs of points. The x's called the features, the y called the labels. In their figure, they have an arrow like this because the f determines the y's from the x's. Each x sub I is equal to, should be each y sub I is equal to f of x sub I, like that. That's how this f determines all of the training data. And then in the actual learning procedure, there's some sort of learning algorithm, which they call like a fancy script A. In our example so far, this is that perceptron learning algorithm. And there's also, as part of the learning algorithm, there's this hypothesis class, which they use the fancy script H for. And every model is determined both by your hypothesis class, the set of all possible functions that you're looking for, and the learning algorithm, which you use to determine which one of those functions to use. So those two things together are the model. Anytime you're specifying some sort of learning problem, you have to specify both the algorithm you're using and that space that you're searching over. For the perceptron algorithm, this hypothesis class, this space was the space of all linear functions. And we use those two things together to generate our final hypothesis, which they always use G for. G is contained in this set H. So it's all the same notation that we had last time, just sort of put into a picture format with arrows talking about how it all relates to each other. And everything in blue right here corresponds to figure 1.2 from the book. Down below this figure, it turns out there's 3 different ways where learning can fail us somehow. 3 different things that can go wrong with learning. Down below, I'll draw these 3 different figures and what they are. So far, we've seen one of those. So 3 ways learning can go wrong. Things can go wrong. What we talked about last time, the way that things can go wrong is if we have the wrong hypothesis class. So if we have, say, the pluses and the circles, this is the classic example, the one that should be ingrained in your head about how something can go wrong right here. That there's no linear classifier, no W star, no perceptron that can separate the minuses from the plus, because they're just you can't separate a circle with a line. And so this failure mode, number 1 right here, is the wrong hypothesis class. And this exactly corresponds to the information in this blue figure up here, all the notation that we have. For the thing that we've seen up to this point, with the formalism we've seen up to this point, this is the only thing that can go wrong. So it's a good spot to pause. Anybody have questions while people are catching up with the note writing? Yeah. So when I say wrong H right here, I do mean the capital H. I do mean the wrong hypothesis class. So this the H right here corresponds to the perceptron hypothesis class that I drew right here. This perceptron. And there is no perceptron that can correctly classify this data. We saw other examples of data where perceptrons could classify the data, but here they can't. And so if we had data like this, we'd have to pick a different hypothesis class somehow. In the real world, though, there's another thing that can go wrong. We might already have the correct data point or the correct hypothesis class. And so let's say our training data looks something like this. Our training data looks something like this. And so if we have data like this, I might select this as my W star. And that looks great on this set of training data. But if the real data was actually if we continued gathering more and more data and actually had the case where like everything over here could be pluses and everything over here minuses. So this one up here is a small data set. This one down here is a larger data set. Then clearly down here, the W star that I want would be like the straight vertical line up here. And this W star on the larger data set would be a good one on this small data set. If I were to use the same vertical line up here, I would also be getting 0 error. I would also be classifying everything correctly. But when I only had the small data, it looked like this one right here might be a better one. But the fact that I have a larger data set tells me that this is actually the correct W star. So the problem right here, the problem number 2, is that we only have finite data. The formalism about how we talk about this in notation, I'm going to scroll up a little bit back to this figure up here, is that they add a box. I'm going to draw it in green because it's now part of their new section. This is part of their figure 1.9 right here. And there's an unknown distribution of data. Unknown distribution of data, which they call P of X. So P standing for the probability, and every X data point has some chance of being selected. And this is also how we're using to generate our training data, that these X sub i's are somehow sampled from this unknown distribution up here. And then after we do that sampling, we use this formula to compute the Y's. And so because we have this unknown distribution, the data can potentially be anywhere, but we only have a finite sample of it. We now have this new type of error that can be introduced to our problem, where even though we have a perfect classifier on a small data set, it might not be a perfect classifier on the true larger data set if we keep sampling from that distribution. In their figure 1.9, they also have an arrow coming down here that this probability affects how we compare. Our goal is to have our final G to be approximately equal to F. And we'll see that this distribution is going to affect how we do this comparison here in a little bit. The last problem is even if we have like infinite data somehow, even if we have infinite data, so I'll draw that like here's basically using this as my example of infinite data. And so the optimal classifier still looks like this. Even if we have infinite data, there might be noise in our data set somehow. And so in blue here, so that it's possible to see it, I'm going to draw some negatives over here. That there might just, no matter what we do, be some chance of negatives appearing with the positives and positives appearing with the negatives. I think the bank example, the credit loan example, is has a natural example of this built in. No matter how much data we have about a person, we don't know what the economy is going to look like 10 years from now, and so it's impossible to predict whether they'll be able to pay off their loan or not. They might get fired. That's something that only the future knows. There's no way for us to know that, and so there's some potential natural uncertainty in the data. And this is our third problem. Somehow a natural uncertainty means that it's impossible to get zero error. Impossible to get zero error. No matter what you do when you're trying to predict credit for people, no matter how much information you have, you're never going to be able to determine things perfectly, because whether somebody pays back or not depends on future things that nobody can possibly know. And so the way that gets modeled formally up here is that our, and I'll do this now in red, the final figure up here, red, is that this f is going to have some noise term added to it. They also write that the f is now a probability distribution, the probability of y given x. But there's this somehow fundamental noise over here, so that in some sense, every time I run this f function, I have to apply this noise to it, and it may or may not actually be the correct result. What we're looking at next, over the next couple of weeks, is the relationship between all three of these different problems. How can we determine whether, like, given a particular problem, which one of these is the actual problem with, or if given a particular learning problem, and we have some error associated with it, how can we determine which of these is causing the error and how to fix it? If it's just natural uncertainty, there's not much we can do. But if it's just the finite data, then maybe we can switch things around using a different hypothesis class or adjusting things in a certain way to make the problem more tractable. So this is all the notation. The key thing to take away from here is the notation and getting the intuition about how things relate to each other. This notation right here is not something that I'm ever going to ask you, like, formally to, like, draw this picture or something like that, but you'll need to have a good intuitive sense of how all these terms relate to each other in order to go on to the next sort of problems that we're doing. Are there any questions about these error methods or these failure modes? And yes, buddy. Yes, the question is, why is there this error right here? And the answer is that we're actually going to be using this unknown distribution to determine how close G and F are to each other. Yeah, our measurement of how good they are is going to depend on this. And I think that takes us directly into the next problem. Yes, it does. So we'll go ahead and take a look at that. So there's two. So in problem 3 here, or the idea of problem 3 is that in a typical machine learning setup, we often have 2 data sets that we work with, a training data set and a test data set. We would run our learning algorithm, whatever it is, like the perceptron learning algorithm, on the training data set and evaluate it on the testing data set. And in this problem, we're going to think about why that's the case, why we do things that way. And we'll actually also talk about how big should your training and test data sets be in order to get good, accurate results. There's 2 definitions here, the in-sample error and the out-of-sample error, which will be crucial to memorize. These, in the book, they have a very, very gentle introduction to all of these terms right here. So I'm going to go a little bit fast. If this stuff feels a little bit fast, then the book's introduction, I think, is pretty gentle and you might find more helpful. But so this in-sample error right here is defined E sub n of H. It's something that's going to depend on our particular hypothesis. Anytime we use in the book that lowercase h, it's some hypothesis that we don't know what it is. The G is the hypothesis that we've learned. So E n of h, 1 over n, sum from I equals 1 to n of this weird square bracket thing, h of x sub I not equal to y sub I, like that. So first, what does this square bracket mean? It means that if the thing inside of it is true, then you'll get 1. If the thing inside of it is false, then 0. So square bracket of true equals 1. Square bracket of false equals 0. Statisticians often talk about the accuracy of models. You may have seen people talking about the accuracy of models before. The accuracy would be if these two things are equal to each other, if the hypothesis that we're using is, correctly predicts our output. But machine learning people, we are pessimists, and so we talk about the error usually. And so we focus on when they're different from each other and try to minimize the error. In the book, a little notational thing is they don't directly say yi right here. They say f of x sub I. And by definition, we know that the f of x sub I is supposed to be equal to the y sub I, but we don't actually have access to this f function. It's not something that we can calculate. So if you were to try to calculate this in-sample error right here, you would be comparing to the y sub I, something that's given to us. And then the question about how does the unknown distribution affect our understanding of comparing f to g, that comes in this out of sample error, E out of h, and that's defined to be equal to p h of x not equal to f of x. This p right here is that same distribution, that unknown distribution on the data points. And so for whatever our unknown distribution on the data points are, we want these two things, we want them to be equal to each other, but we're measuring how often they're not equal to each other. The intuition behind E out, this will be a very informal thing. The intuition is that as the n goes to infinity, the limit as n goes to infinity of E n of h, that'll be equal to E out of h. So as this goes to infinity, as you get more and more infinite number of samples, then these two quantities will converge together. It's not technically a formal thing though, because technically this is going to be over an uncountably infinite set, and this thing here is only countably infinite. These two quantities right here are going to be things that you will have to memorize over the next couple of weeks. We're going to be using them so much that you will just have them memorized without actually necessarily having to sit down and memorize them. But yeah, these are going to be very critical for us. Any questions about what they mean, what their definitions are? Yes. Question is, what is this h? Yeah, so the question is here exactly what is h? H is in fact a function. H is a function from our whatever our x's are into whatever our y's are. And in particular, it's a member of whatever the hypothesis class is that we're looking at. So the hypothesis class, the script h thing, that is a set of functions. If, again, for the example of the perceptron learning algorithm, it's the set of all possible linear functions. And here we're trying to, the in-sample error and the out-of-sample error are defined for one particular of those h functions. So like after I've run my PLA algorithm, I get some hypothesis g out, some function g. Anytime you hear me say the word hypothesis, you could just think function. Anytime I get a hypothesis out of the perceptron learning algorithm, I can plug it in here and it'll evaluate how well it does. Good question. Okay. So there's a class on data mining. One of the things that's sort of a subcomponent of data mining is machine learning. And one of the things that's always hard to explain to people is exactly what is the difference between data mining and machine learning. And this stuff in problem 2 right here gets us into the first sort of weeds about exactly what is machine learning. The main goal of machine learning, anybody who says they do machine learning research, what they're doing is they are in the abstract comparing this E in to E out and coming up with abstract formulas that compare those two things together. One of the most important of those abstract formulas, which we will be using, is this inequality down here, this theorem, which is called Hufting's inequality. If this were a statistics course, we would be actually like going through and proving this inequality. If you've taken statistics already, you probably have proved this inequality. You've definitely proved some version of this. Hufting's inequality is an example of the central limit theorem. The CLT, the central limit theorem. So statisticians are people who are interested in proving these sorts of things. Machine learning people also interested in proving these sorts of algorithms or these sorts of theorems, but they're specifically in the context of the in-sample and the out-of-sample error. So very close relationship between statistics and machine learning. For us in this course, we're not going to prove any of these theorems. We're going to just state them. And then the idea of data mining is like, how can we actually use these to somehow really get good analysis out of our data? So let's walk through the statement of this theorem step by step. This theorem is going to be something that you will have to have perfectly memorized. And that midterm quiz for this second midterm is going to involve this inequality right here, this theorem statement. So if you're not busy with the current midterm, then you want to get started on the next one. Memorizing this is the next thing to do. So we have A1 up to AN, different independent events that are happening, random variables. They're all satisfying that they come between 0 and 1. This new character right here, that thing pronounced new in U, this thing here pronounced mu. Nu is our sample accuracy, our sample average. And then the mu is the actual true average of something. And so what this is asking right here, describe the shape of this distribution defined by this inequality. I'm going to draw out a PDF, a density function that will look like this. We'll make it a little bit wider. Here's our 0 point on the x-axis. We'll say this point over here is 1. All of the a values must come between 0 and 1. And so because of that, our nu and our mu values must also come between 0 and 1 because they're somehow averages of these a values. Let's say that right here is the mu value. This is our true average, the thing that we are interested in knowing about, but we can't know the true average because we don't actually know the distribution. We don't have this f function. We don't have the ground truth of our problem. So all we have access to is our samples. And when we gather all those samples together, we get some value nu. And the distribution of nu is going to be a Gaussian distribution that looks something like that. Relatively flat, close to mu, and then very, very close to 0, going farther away from mu. This is the PDF or density function of nu. That v thing is this Greek nu, the Greek v up there. And the variance of this, so if that's our mean, somehow the variance is going to be equal to 1 divided by n. This quantity up here, if you squint, looked up the definition of the Gaussian in Wikipedia, you'd see that this is actually a Gaussian density right here. And if you plugged in things for the variance, you'd find that the variance comes out to be 1 over n. The important thing about this, the important thing for our purposes, is that as it increases, I'll draw another one of these densities that looks maybe a tighter density like that. So now here's our mu. As the in value increases, so this will be a for high in. Then our distribution is going to get tighter and tighter, converge more and more close to the mu value right here. And that'll be good. It means that we'll be able to somehow have a better estimate for what the what our true, in this case, average is. Any questions about that? Okay, so what our next steps here are going to be to somehow use this this Hufting inequality with these two definitions of our in-sample error and our out-of-sample error up here. We'll be plugging those, oh dear, where did I go? We'll be plugging these definitions right here into the Hufting inequality, seeing what sort of bounds we can get on the statistical performance of our algorithm. And we're out of time for today, so we'll do that next time and after the midterm. If people have questions about this stuff or questions about the midterm, then I'll stick around as long as people have questions. Otherwise, I will either see you tomorrow morning in the review session, 10 a.m. to noon, after which the midterm will be posted. So good luck to you all on the midterm if I don't see you before then.
I just had a couple of questions about the true or false questions. So